Yeah.
Very excited about it.
All right. So thank you everybody for coming. I'm super excited to hear this and hear all the chat that goes on afterwards. It's the Go Meetup for September. I do want to put a quick warning because it's not always clear if you've ever listened to any of our friends to microphones. The whole room is wired for sound and it will zero in on you. If you think you're whispering, you might be. You'll still be loud and clear in the room. So, you're welcome to do it. I'm just giving you a fair warning. They will all hear you and you will go up. We have all these links here at the bottom. One of the ones there, and the big one is the Forge Slack. I always call out specifically the jobs channel, but there's also places for hiring. There's places to go. There's places for cloud native. All things open source and cloud native are welcome to be discussed there. So if you want to join us on there, we'd be happy to have you. If you want to speak here, we've sort of meshed our pipeline with Web3 In Go Utah. So the paper call.io is Web3 In Go Utah. But if you submit there, that's the way to get pipelined in here. Or you can just go straight up on Slack and just hit me or anybody else up, or just hit me up on LinkedIn. So we got our crew figured it out. We're actually all the way through. I'm super excited. We are jam-packed every single month this year. So we're just looking forward next year or January on. There's also Go West coming up, really probably too fast for Mariah to be happy. It's coming up in just about a month. And there are, sorry, what was that?
It's 47 days.
7 days, there you go. There are still lightning speaker talks?
Yeah, lightning talks. You can register for lightning talks.
Okay.
We're gonna do those. We're just taking a roll call, and we'll just go through the list on that day. Tickets are for sale. We've sold 50 of our 150 in-person tickets, so you can get more tickets to come in person, or you can attend online for free.
It'll be here from the first.
It will be here at least. So, because we have the best facilities in the entire state, we tested all of them.
So awesome. Yep, that's coming up. Feel free to submit a talk or in person or online. It's always a fun. And that's it. That's all I have for housekeeping, just bare bones stuff. I'm gonna hand it over to Mike, who is gonna come. Oh, I was gonna say the one thing I want to say about Mike is I have a Google story that the last meme that he created at Google was the Badger meme. So that alone would be a bunch of confidence in sort of like he's also got the beach. If you've got a massive beard or a good meme reference.
I think that they're having sound issues on the
Meetup?
meetup.
Oh.
You try muting that on the screen and unmuting it. If not,
There we go. How's that for people online?
it's gonna come through the recording choppy if they can still hear it choppy.
Let's go one more time. Anybody want to give me a thumbs up or better? Okay. Well, that's the only thing I have to do. So hopefully that works. If not, we've got a backup recording.
That's all we've got right now. Yeah, it's because otherwise.
Okay. Thanks, Mike.
Thank you. Take this presentation here. Okay, I'm Mike Stay. I'm the CTO of Pyrofex Corporation. We started out back in 2016 working on software for running distributed computation in data centers, but very quickly discovered that while we could convince people of our position and the need for our software, if we could talk to them, we didn't have to convince anybody about anything with respect to cryptocurrency. So quickly got into that, and after a while.
Mike, are you sharing your screen? We're not seeing
It
it.
should be. Is it not?
I saw a second ago a toast
for a
that
second,
said you
yeah.
left the meeting.
Okay, let me try to rejoin. Join. Send.
Yep, you're back.
Yep.
And there we go.
There we go.
Okay, cool. Yeah, so now we're doing this layer one cryptocurrency platform called Silvermint. But we're developing the whole thing in Go, and we're also going to have our smart contract language be based on Go. So to give you some idea of what the challenges are, got this little list of things here. People doing attacks, there are lots of the obvious things, right? You can send someone a phishing email and they give you their password information, go to a site that you control. You can hack the front end servers to embed new content so it looks more convincing when it's not coming from the server you trust. You can hack into the backend server to get the private keys. Nakamoto coefficient. So how many machines do you have to compromise to take over the network? Well, Ronin only required 5, and so they got away with $610 million by corrupting those 5 machines. Scams, you set up a fake company with fake CTO and fake ideas about what to do. People dump a whole bunch of money in and walk away with it, and nobody sees them again. One of them was a fake job offer from a North Korean group. As part of that interview process, they sent them a PDF with an exploit to get access to their network. From the internal network, they compromised private keys and were able to steal a few $100,000. Bugs like not properly checking the signatures. The attack in February 2022 that netted $323 million on the Wormhole Bridge was this sequence of things. So there was this particular instruction that didn't check the signature, which allowed them to produce what they called a set of signatures. And that signature set was sent to post VAA, and the VAA was used to mint Ethereum wrappers on Solana, and the Ethereum wrappers were exchanged over the Solana bridge for actual Ethereum. Poly Network from last year, $600 million. But the white hat returned it. There was a contract that had authority that would check signatures and make sure everything was okay before it handed off control over to this other thing that would handle the money. But the way they tried to enforce that only the right contracts could call into this one was by invoking a specific method. But because EVM doesn't call things by name, but rather by hash, and the hash is only 32 bits, the attacker could simply brute force their method name until it had the right hash, and then could take control when they invoked this thing. These are all hard to defend against, but we have a bunch of other bugs recently that seem to be easier. So one was an overflow bug. Back in 2010, when Bitcoin was just getting going, an attacker minted 184 billion Bitcoin because of an overflow bug. Bitcoin did a soft fork to recover. The DAO hack in 2016, the DAO was a distributed autonomous organization. So people would pay in and acquire voting rights. They weren't stock really, because there wasn't a corporation that was created. It was just the ability to vote using these protocols. And then they would decide how to spend the money that was deposited into the DAO. This one was named the DAO. And at the time, it had 14% of all Ethereum that had been minted. The reentrancy bug that I'll get to in a minute, a deeper analysis, meant that the entire quantity of money that had been deposited into the DAO was stolen there. They did a hard fork to recover, and now there's Ethereum and Ethereum Classic. Ethereum Classic was subject to a 51% attack. That is, they had more computing power than the rest of the network combined and ran the fork ahead faster. And because machines always build on the longest fork, they started building on the new one, and it revoked all of those transactions on ETC. Another reentrancy bug, the optimism bridge in February this year. Grey Hat hacker discovered it and began exploiting it, and then they paid him off with $2 million. Another reentrancy bug, July of this year, the Omni bridge. Black Hat cashed in his wrapped Ethereum for 1.4 million. So overflow bugs, reentrancy bugs in particular, have been the source of a lot of stolen money. And while it's expensive to have developers do proofs on code, really expensive, it is nowhere near as expensive as losing $610 million to an attack. So there is finally enough money and impetus behind proving programs correct that it starts making sense to do so on the blockchain. So that's the opportunity we've got right now, and the opportunity that we're considering here. So this is how the reentrancy attack worked. We've got this wallet interface where you can ask for how much money is in the wallet and put some money in. Withdraw wallet means you can also ask to withdraw the wallet, the money from it. And then this is roughly what the DAO contract looked like. So there was a wallet from which funds could be withdrawn. And internally, it kept a map from accounts to balances. So how many Ethereum were in this account belonging to this public key. So anybody could deposit funds into the DAO, and this would keep track of it. But the money itself was part of the contract. I put it here as part of the data structure, but on Ethereum, every contract can own funds, and that's the one I'm talking about here. So to deposit money, you hand it your public key, which is part of the signed message that you send to the contract. And the Ethereum you're depositing, it puts it in its own wallet and credits your account. When you withdraw, you send a message signed with your public key, say, I want to withdraw this much, and when it comes out, put it here. So it checks. Do you have that much? If so, withdraw the Ethereum, deposit it in the receiver's wallet, and decrement your account. And here's total. It'll say what the total balance is of the DAO's holdings. So that looks at first glance reasonable. But the problem is when money is deposited in an Ethereum contract, it triggers the execution of code. And that code can call back into the original DAO contract. So here it says, when you receive some money, stash it away. And if there's any money left in the contract, call withdraw again with 1. Now look at the logic here. First it does the withdrawal, and then it deposits it in the attacker's account, but doesn't deduct this until this one returns. So as long as there's enough stack depth for you to call over and over and over again, it's never going to hit this deduction of the amount. Instead, it's cleaning out the DAO's wallet. That's how they did it. Once the DAO was empty, this withdrawal thing stopped happening. So what can you do about it? Well, you can swap the order of these two lines. You can notice that in certain asynchronous or concurrent situations, it doesn't work. So if we replace the receiver wallet with some asynchronous thing, like a channel on which we can send a message, and instead of calling deposit directly, we send a message saying, here's some money to deposit, go do it on your own time. Then this might succeed where the other one didn't, because when you send an asynchronous message, this runs immediately. So when you're doing it with threads, it's possible for a race condition to happen, right? Maybe you get another call into the wallet before your amount is deducted. If you're doing it in something like Node.js, where it's a concurrent system of communicating event loops, where only one message gets processed. When it's finished, then it moves on to the next one. Then this necessarily happens after the other one. So that's another way to address it. But these are very special cases, right? We would like to be able to reason about our code more precisely more of the time. In this case, one thing that would stop it is to say, for any receiver, account, and amount, the sum of the account balances equals the balance of the wallet. So you can't ever have the sum of the account balances be different than it is in the wallet. In this attack, it keeps withdrawing more and more, even though it's not decrementing any of the balances. So as soon as those are different, or if there's a proof that there exists a receiver for which it causes it to be different, like the one I demonstrated, then we can say, no, this code has a bug. More specifically, we can say for any receiver, account, and amount, either nothing happens, or the balance of the account, the balance of the wallet, both decrease by exactly amount, and the rest of the internal state stays the same. So we would like to be able to prove things like this about the code. The existing ability to do that in Go is pretty much wrapped up in this idea of types as witnesses of properties, of invariants. And so we might construct, for instance, this data type where we guarantee that in order to produce one of these things, the data inside has to be even. So here, the new function sets this private member only after checking that the result is even. Otherwise, it returns an error. This is in the Eiffel style of what they call contract-oriented programming. If you stick in these assertions about data at runtime, you can guarantee, well, it passed this assertion before getting to this code, it passed this assertion before returning this result. And so you can do a lot of powerful reasoning that way, but it's all at runtime. Now on the blockchain, that's fine, right? You can submit a transaction and the transaction fails. Better safe than sorry. You don't lose your hundreds of millions of dollars. But Google and Facebook and Microsoft all developed static type systems for JavaScript because they wanted to prove things about their code before deploying it, putting it in front of the public. And so as a systems programming language, we would like to be able to prove more things about our code before deploying them to the public. And so that's really our goal with this idea. So we've got this set of language extensions for Go. We decided to use Go for various reasons. We wanted to give programmers the ability to formally verify their code. So we looked at things like Agda and Coq and Bell and all those theorem provers, but there's no real developer community around those. It's largely academics doing formalization of proofs as opposed to developers trying to prove things about their code. We didn't want to have to develop an entire ecosystem, right? Haskell is awesome, but it's hard for most programmers to get into. We would have to write compilers, libraries, editors, debuggers, package management, et cetera, around a new language. And there's the practical fact that of the top 40 programming languages, 38 of them are eager and imperative. So if we want to get the existing community of developers to use this and be comfortable with it, choosing an eager imperative language is the way to go. And so we chose Go because it's an awesome language, right? It's relatively simple, it's memory safe, it's strictly typed language, and the inheritance model is very, very simple. So we thought it was appropriate. To formally verify programs, we're using Microsoft's Z3 tool, which is a satisfiability modulo theory. So satisfiability is an NP-complete problem. It's as hard a problem as is easy to check the answer. So the idea of NP complete is that you can easily check an answer, but it's hard to guess. There are exponentially many possibilities that it could be. So satisfiability is choosing an input that makes a circuit output true. Satisfiability modulo theories says, well, we've got all of this stuff that isn't just and or and NAND gates. We've got addition, we've got algebraic data types, we've got floating point with IEEE 754. We have all of these different things, kinds of data that we're working with, and we would like to be able to declare rules about them in the same way that we reason about bits. And so satisfiability modulo theories lets you come in and say, here are some assertions about the code that I'm actually writing, help me figure them out. Microsoft produced Z3, and they're also the power behind the Daphne language. ZZ is a C-like language where they use Z3 for proving that you don't get any of the C undefined behavior that exists in the specification. So one of the first things we missed were algebraic data types. There is no sum type yet defined in Go other than declaring an interface and implementing a bunch of structs. But in order to check that you've covered all of the cases, you need to know which structs can implement that interface, which means you need to be able to prevent others from implementing that interface so that when you get to your type switch, you know that you've covered all your bases. So what we do is transpile. We introduced into the Go compiler a new keyword called simsum. All of our additions have this sim underscore prefix. It's a placeholder for the moment. We may choose to change that later. But they're generic, thanks to Go 118. And then we can use those generics within this set of structures inside. Then it gets transpiled to an interface with a method that has a randomly generated name. So that random generation means that if you declare an ADT at the top of your file, you can't predict what that's going to get transpiled to and break the invariant later on in the same file. Of course, if you declare it in its own package, it's hidden, so there's nothing you can do there. But that was necessary for maintaining the integrity of the data structure. So then it outputs the new structs, which inherit the generic parameters from the enclosing sum. It says these implement that method, automatically generates those. Not denoted, I mean, not in this document, but it also outputs transform and reduce methods. Transform is what a functional programmer would call map. It takes, for instance, a list of things and maps a function over the top of it. Transform is the keyword that, or the word that C++ uses. Since map was already a keyword in Go, we chose transform. Reduce is the same as fold. So by looking at the structure of the ADT, we can automatically derive the code to implement those specific to that data structure and parametric in that parameter. So you avoid an enormous amount of boilerplate. You're guaranteed correct implementations of these. You can check that you are being comprehensive in your cases, so you're not going to get a runtime error. The next thing we're doing is using Z3 to improve the type system. So Go 118 introduced generics based on Hindley-Milner. These are what in the literature are called intrinsic or church types. If you have an int, it is not a string. They don't overlap. They're different things like nouns and verbs. They're different almost grammatically. Whereas we can use Z3 assertions to augment the type system with what are called extrinsic or Curry types. With Curry types, it makes use of the duality between having a subset and a function from a set into a subobject classifier. So if you have a function from x to 2, that is the two-element set true and false, the elements that map to true are in the subset, the elements that map to false are out of the subset. So you can take a type that includes all your values. For example, in JavaScript, everything is a JavaScript value. But then you can use contracts, like the ones I showed with isEven, to assert properties of these values. And that is what gets called a type in the system. So using this sort of thing, we can do examples like the add event listener API in the document object model in the browser. So with add event listener, you say, I want to listen for clicks, and I expect to get a mouse event when someone clicks. And I want to listen for keyboard events when people hit, a slash in Gmail. It should take me to my search box. So depending on the first parameter, whether that string is click or key down or key press, I want to have the second parameter, which is a function that handles the result, be of the correct type. That I shouldn't be able to provide a keyboard handler to the click to try to handle a click event, or a mouse handler to try to handle a keyboard event. And so what you can do then is say, with Z3, we can filter all pairs of strings and handlers and say, I'm only going to accept the ones where the first and the second are coherent, where they match each other. So by filtering in this way, we can add these extra constraints on the existing types to do cool stuff. And this is what in math is called a sigma type, which is a kind of dependent type. To get the full strength of Z3, we'll essentially need to write a compiler from Go into Z3. We'll have to define a virtual machine that can run Go programs, keep track of the stack and the heap and all of the associated stuff about where you are in the program and whatever is necessary in order to run abstractly a Go program. That'll be the data structure, and then there will be rewrite rules that modify that data structure according to the semantics of the language. So once we've got this full spec, we can then do reasoning about which transitions are possible, what program states we're able to reach. Symmetry is intended to run on the blockchain. Got lots of different computers, but they, rather than being something like a data center where you're splitting up a job into 1,000 parts and having them all worked on in parallel, on the blockchain, everybody does all the work. It's massive replication rather than distributed computation. And so in order to replicate this, we have to have the code be deterministic. So then there are a bunch of things that aren't deterministic in Go. For example, iterating over maps or sending messages over channels. We have to figure out how we're going to handle those. Layers are really the most developed part of symmetry at the moment. If you're familiar with any functional programming languages like Haskell, you implement state by simulating it using what's called a monad. So essentially you have some part of your data structure be the state that's being acted on, and you have another part that is the data that you're passing into your function, and it combines those, runs through the thing, updates the state, and produces the result, and you get the output of the function and the new state that's being worked on. When you're in an imperative side effectful language like Go, there's no way to capture that external state. And so it turns out that there's a duality, and there's this beautiful paper called Recovering Purity. Oh, let me put that up just to say. Recovering Purity with comonads and capabilities. So rather than use a monad to simulate state, you use a comonad to recover purity. And the way it works is there's a language construct that's checked at compile time that says, when I create a value of this type, the value passed in has to satisfy these conditions. And in symmetry, we're most concerned with deviations from purely functional behavior. So concurrency, assignment, mutation, all of these kinds of things are deviations from purely functional behavior. And so What we check at the call site is that the code that is running there has no free variables that that close over other state that can be mutated. So first there's a grammatical check. We check the syntax within that, whether it uses assignment, whether it uses iterating over maps, whether it uses increment, decrement, whether it uses the send and receive operators and so on. But then we also look at the free variables. And if you invoke a function, that function must previously have been marked to close over no capabilities, or it has to be passed in as a parameter to the nearest enclosing function. So if I give you a function that has been marked as core, you know that you can invoke that and it won't be able to cause any side effects except by means of the objects that you pass in. And so if you pass in a logger, the only side effect it can cause is by invoking the log method on the logger. You know it's not going to print to the console, you know it's not going to send network messages. You can bound the authority of the code by looking at what arguments you pass to the code. And so that gives you an enormous amount of power in reasoning about the behavior of a code and checking that it does exactly what you want. So we have three different layers. There's core, which isn't precisely purely functional, but it's close. The deviation there is, suppose you have a getter setter pair. The getter can't change anything. All it does is return the current value that it's closing over. The setter, however, could change the value that it returns. And so if it were purely functional, it would always return the same value because you don't give it any arguments. But in this case, it could return different values. But that's the extent of the deviation from it. We could go all the way to purely functional, but we want to see if there's demand for that first. The second layer is called stateful. That one is single threaded, and then full has the full power of Go. So those are the main ideas that are in the language extensions. In the Silvermint platform itself, what constitutes a smart contract? If you look at something like SUI with their Move VM, they treat their state very much like a database. So you acquire locks on objects, you move them around, the transaction finishes, they're unlocked, and it proceeds that way. We are treating our contracts more like servers on a virtual network. So you set up a contract, and within that contract are a bunch of objects living in what's effectively the same memory space. So you can invoke an object within that memory space, and it can communicate synchronously with the other objects within it. But as soon as it wants to talk to some other contract, that's an asynchronous call. And so you run for a while, the turn finishes, it queues up some messages to be delivered. And if the turn succeeds, there's no error, then those messages are delivered on the next turn. And they come, you have to equip those messages with gas to pay for their processing further on. So that's our model of execution on the Silvermint platform. I could talk about consensus and how we make sure that all these things run quickly with our consensus algorithm, but I'll save that for later if you're interested. So that's where we're at. If you'd like to see what it looks like, we have the symmetry layer spec here. But we also have, where is it? This one. So this is an example. Here we say, my sum is declared to be core. So if you tried to compile this here, adding this integer, adding B to A would cause a side effect. And so the compiler would flag that and say, no, this is not in core. You claimed it was, but then you used this. More layers. Let me see if I can zoom this in a bit here. Here we have an interface whose methods are declared to be core. So dog is this interface. Poodle has a name, and it implements the methods with the core tag. And so it verifies that this implementation doesn't close over any capabilities. Terrier here is another struct that without these keywords would implement this interface. But because we've marked this one as stateful, the compiler says, nope, you're trying to do a stateful thing when the interface wants core. And so that happens here on line 28 when you're trying to say that your dog, which is a dog, is assigned to Terrier. So it only checks that once there's a struct type assigned to an interface type. And finally, here's an example of the transpilation. And this was an example of the assertion. So one of the exploits, the Bitcoin exploit from 2010 I talked about, was an overflow error. So here, sometimes we pretend that we have integer types in Go, but we implement it using something that wraps around. And so here, this is asserting that if I add 1 to A and 1 to B, the resulting numbers are greater than what we started with. And so then Z3 can come along and say, nope, if you've got the largest possible signed int, then if you add 1 to it, you get the smallest possible signed int. And we'll say you've got an overflow error and catch that sort of thing. It does it by transpiling it to Z3 and providing a model that then it can report in the errors. So we hope that by providing these tools, we'll be able to write our own code better because the Silvermint node is being written in Go. We hope to be able to use our own tools to prove that our implementation is correct, but also that the smart contract authors can write code that's not going to lose them hundreds of millions of dollars when they deploy it. Thanks for your attention. Any questions? Yeah.
So would you classify this very similar then to TypeScript, where you're spending a lot of time and effort building a better type system and making it so that before you even try to press the run button, the computer can give you back results? Or are there actual runtime changes as well, or things when you're executing the code that you're also doing? Is this all up front and you can spit out code that could run on an existing chain or an existing smart contract as well?
So great question. So is all of this compile time or is some of it runtime? Certainly when we first deploy this, because we're concerned with safety, our smart contracts will leave in the assertions to be runtime assertions. We intend to prove it in advance, so those assertions should never fail. But if there's some possibility that there's an implementation bug somewhere, better safe than sorry. Once we become more confident in that, we'll remove the runtime assertions. As far as using it as a systems programming language, we generally want to do as much as possible in advance. Runtime errors in a deployed system mean somebody gets paged and has to come in and scramble to fix the thing. So our goal is to make it easier for people to prove their code correct. We're not going to require that anybody do anything. Symmetry is a language extension. It's a proper superset of Go. So every Go program is a symmetry program. Modulo unsafe, right? We may forbid importing unsafe in certain parts of the Reflect API that let you twiddle with things under the hood. But other than that, everything that is Go is symmetry. And so we're just giving these extra tools to allow people to become more confident in advance of their the correctness of their code. Any other questions? Yeah.
So why Z3? Why not like Coq or one of the other more formality adjacent worlds? If you're going for provability, I guess.
Yeah, so with Coq, you basically have to learn to program in Coq. If we were going to adopt Coq, we would say, well, we might as well take Coq as our programming language and use that. We think that that is an undue burden. There may be those who really, really want to be sure, and Coq is certainly the appropriate way to go for that when you're willing to pay any price upfront to make sure that your stuff is okay. And you can certainly start with Coq, prove that something is correct, and then output Go code that behaves properly to deploy on the chain. What we want, we have to balance this idea of making it accessible to the programmers and the business proposition of getting people to use the chain and that. At the same time, we would like to make it possible to do better than what you can currently do in Go. And so we think we've struck a reasonable balance there.
Going for kind of the Pareto, meet 80% of the people's needs and save that safety, and there'll still be some risk, but it'll be much more mitigated, that sort of thing.
Because you can deploy Go code to the chain. We're not preventing you from shooting yourself in the foot, but we'd like to give you as many tools as possible to help you write good code. Okay. Yeah.
If Go 3 for hypotheticals had something like annotations or decorators, could you see something like this being upstreamed into actual Go if all you need is the ability to kind of annotate things? Like you could use comments now, but it would make writing it much more difficult if it had the first class features like .NET or some of the others do that have built style cop and everything around that. Do you see this kind of?
Sure. I mean, if at some point Go adopts any of these features or makes it easier to transpile into them, we can deprecate the feature in symmetry and just say, do it that way in Go, and still support the transpilation of the symmetry code into that new feature. So it'll be more efficient and so on.
Are there any benefits you could see, like low hanging fruit for somebody that wanted this in a actual Go program, or it's not that hard to fork to your version of Go anyways and take that route?
The implementation we're building is a transpiler. So we're using Go's built-in AST manipulation stuff, but we've added new nodes for our language extensions. And the way we process those for SimSum, for instance, is to output only constructs that are in native Go. For the SimAssert here, for instance, we just strip it out entirely because then it's just generating other code that will run and generate a model. So all of the symmetry code eventually produces native Go code, and that will run. Did that answer your question? Any others? Great. Thank you very much for your time.
Has anybody ever done any formal verification of your projects?
Yes.
Yeah. And use Coq?
No, we were using Ada and we had to do it by hand, so
Okay.
I don't recommend that way.
No.
That was many years ago.
Cool.
Awesome. Well, thanks again. And we'll stop the recording and once feel free to grab more pizza and hang out.
The real conversation.
Off the record.
Off the record.